let me talk a little more about prime ideals. R is a commutative ring with 1, as it has been for a while now. A proper ideal P in R, proper just means that it's not equal to the whole ring R. A proper ideal P in R is called a prime ideal if whenever A times B is in P, then either A is in P or B is in P, for all A and B in the ring R. That's the definition, and this is like the definition of a prime number. We have seen that if you define the divisibility among ideals properly. And an element is called a prime element if the ideal that it generates, the principal ideal that it generates, which is denoted by parenthesis P, is a prime ideal. So if you unpack what that definition says, it says that some element is a prime element if whenever the element divides the product of two elements of the ring, then it must divide one of them, which is the basic property of a prime number. Maybe here I should say non-zero. I've not been exactly careful here. A non-zero element is a prime if and only if this property holds. I mean, the divisibility is not really defined for the zero element, but this definition still makes sense. So let me go through some examples of prime ideals again. If you recall, we had a lemma which said that an ideal is a maximal ideal if and only if R mod M is a field, and a lemma that said that an ideal is a prime ideal if and only if R mod P is a domain. And since fields are certainly domains, maximal ideals are certainly prime. We'll see that the converse is not necessarily true. So some examples of primes would be, of course, the maximal ideals, but there are more. So in Z, primes ideals in Z are the ideal generated by the prime numbers, these, and I think I missed saying this last time, the zero ideal, meaning, so in fact, notice zero ideal is prime if and only if R is a domain. Because what does the zero ideal being prime mean? It just says that when AB in 0, this is same as saying AB is 0. So the condition for being a prime ideal just says that if A times B is 0, then either A is 0 or B is 0, which is exactly saying that R is a domain. Okay, so there's one prime ideal for each prime number, and then there is this prime ideal 0. All these guys are maximal, but this one is not, because this one is properly contained in either of any of these. So that's the prime ideals in Z. Prime ideals in Fx, F field as always, are the ideals generated by irreducible polynomials, and the 0 one, again because Fx is a domain as well. This we haven't quite proved, we will soon. Then if you want to see some example of a prime ideal that is not maximal, you have to go to at least two variable polynomial ring or something like that. So if you take Fxy, the prime ideals are rather interesting. Some the ideals generated by xy, and then the ideal generated just by x are prime. This much we have seen last time. So this one is maximal. This one is not maximal. Yeah, because this ideal properly contains that ideal. And again, xy here stands for all multiples of x plus all multiples of y, where f and g are arbitrary polynomials in two variables. And similarly, x here stands for all multiples of x. Right. So here is an example of a prime ideal that is not maximal. So I should say here probably the converse does not generally hold. But I want to just do one little lemma here. It says that the converse does hold if you are in a PID. Remember, PID means rings, domains where every ideal is principal, meaning generated by a single element. So prime ideals in, let's be more precise, prime ideals in PID, principal ideal domain, are maximal. This I think I left as an exercise last time. Let's actually do it. And then we'll actually start studying principal ideal domains. So let P be a prime ideal in a PID R. And I want to show that it's a maximal ideal. Maximal means what? Means that if you take a Q which is between P and R, which is also an ideal, then this Q better be either P or R. That there is no ideal in R that is strictly bigger than P but strictly smaller than R. That's what maximal means. So if you have a Q like that, it has to be either P or R. So let's take Q be an ideal such that Q is in between P and R, and I need to show that either Q is P or Q is R. So now since R is a PID, all ideals are principal, so P and Q are principal ideals. We have P is generated by some element and Q is generated by some element for some elements P and Q in the ring. So now I have the ideal P in ideal Q in R. And this P is a prime element because P is a prime ideal, you see. This is a prime ideal, so P is a prime element, the exercise here. And also note, recall, an ideal is in another ideal. Let's put it the other way, the way it was last time. B is a subset of, ideal of B is a subset of A if and only if A divides B. This was the central thing last time. If A divides B, that means B is a multiple of A, which means B, the element B lives in this ideal, which means all multiples of B also live in this ideal. That's one implication, and you can argue the other one as well. Okay, so we have the ideal P is a subset of the ideal Q in R. And I want to show that the ideal in the middle is one of the two on the two ends. Okay, so now note that P is in Q, so P is a multiple of Q. QR for some R in R. But then P divides QR. So P divides QR because P divides P certainly. But now I use the fact that P is a prime ideal, so capital P is a prime ideal, so little p is a prime element. Since little p is a prime element, we have two cases, P divides Q or P divides R. Let's do the two cases separately. Case 1, P divides Q. Then what do I have? Then I have P divides Q, and I also have Q divides P, you see, because P is Q times R. But if P divides Q and Q divides P, then you can see that the ideals are the same. Because P divides Q tells me that the ideal of Q is in the ideal of P, and this tells me that the ideal of P is in the ideal of Q by this property. So in case 1, I have the capital P equals capital Q. And in case 2, what do I get? If P divides R, then what does that mean? That means R is P times something, some S in the ring. So now P is QR, which is QPS then, because R is PS. And since we are in a domain, I can cancel P from both sides, and we get QS equal to 1. So 1 is a multiple of Q, meaning it's in the ideal Q. But if 1 is in the ideal, then the ideal is the whole ring. So in case 1, Q is P, and in case 2, Q is R. And that's what we wanted to prove. So either. So what have we argued? We have argued that, let's just summarize. We have argued that if Q is an ideal such that Q is between P and R, then either Q is P or Q is R. And this says that P is maximal. There is nothing strictly bigger. So we'll start studying PIDs next, PIDs and unique factorization domains.